In the quiet folds of 20th century science, long before cosmology became a spectacle of deep space imagery and billion-pixel telescopes, the first hints of an ancient mystery drifted into human awareness with the gentlest of voices. No thunder, no revelation, only a faint, persistent whisper woven into radio static, a sound that carried the memory of a universe older than its own beginning. It began in 1965 at a modest site in Homedale, New Jersey, where an enormous white horn antenna stood like a solitary guardian of the sky. Its curved metal frame faced the heavens with a kind of monastic discipline. Beneath it, in the grass and autumn wind, two young radio astronomers, Arno Penzias and Robert Wilson, searched for a source of interference that refused to disappear. Bird droppings in the antenna, urban radio contamination, faulty wiring, atmospheric noise. Every possible explanation was tested, and yet the static remained unwavering, indifferent, as though belonging not to Earth, but to time itself. Their measurements revealed radiation at a temperature just above 2.7 Kelvin, a relic glow cooler than any star, fainter than any galaxy. It came from every direction equally, as though the entire sky carried the same ancient breath. They did not yet know that this whisper was the oldest observable light in existence, the cosmic microwave background, the fossil afterglow of a cosmos that had once been unimaginably hot and dense. The discovery would later earn them the Nobel Prize. But in its earliest hours, the signal felt more like an inconvenience. A problem, a noise they could not erase. Yet it would become the first doorway, the first soft, unassuming clue that the universe's origin story concealed deeper complexities than a single, pristine explosion from nothingness. In the decades that followed, the search for cosmic origins moved from quiet radio fields to the heights of the stratosphere and then to the vacuum of space itself. The universe, once studied through ground-based telescopes, was now being interrogated with satellites that sailed above Earth's atmosphere like sentinels of light. The launch of COBE, the Cosmic Background Explorer, in 1989 changed the landscape forever. As the spacecraft drifted over Earth in silent, measured orbits, its detectors mapped the microwave sky with unprecedented precision. What they revealed shocked cosmologists. The background glow was not perfectly smooth. It carried tiny temperature fluctuations, differences of mere millionths of a degree, the seeds from which galaxies, stars, and planets would eventually form. These fluctuations, these primordial wrinkles, were the fingerprints of the early universe. But within them lay something unexpected, patterns that did not align perfectly with predictions, anisotropies that seemed too large, temperature alignments that seemed too ordered, low multipole features, especially in the quadrupole and octupole modes, that hinted at some kind of symmetry or pre-existing structure. It was as though the universe had inherited a memory, a subtle carryover, a faint echo from something that came before. COBE had opened the curtain, but as with all profound discoveries, the act of seeing only deepened the mystery. With the turn of the millennium, new eyes were launched into space. WMAP, the Wilkinson Microwave Anisotropy Probe, reached its orbital perch at the Lagrange L2 point, 1.5 million kilometers from Earth, where gravitational forces balanced into a delicate stillness. From here, suspended between worlds, the spacecraft began to paint the most detailed portrait of the early universe ever created. Its maps revealed astonishing precision, a cosmic tapestry woven with temperature bands of extraordinary subtlety. Yet the more clearly the universe came into view, the stranger it appeared. The peculiar alignments noticed by COBE were confirmed. The hemispherical power asymmetry, a lopsidedness in the early universe, refused to disappear under improved data. The low-L multipoles still looked suspiciously coherent, as though some prior condition had shaped them. Even more unsettling was the cold spot, a vast region of the sky cooler than surrounding areas by a statistically improbable margin. Too large, too deep, too smooth. It suggested structures or influences predating the Big Bang's inflation period, or perhaps an imprint from quantum conditions that had not fully reset. WMAP had pulled the universe into sharp clarity, yet the clarity only sharpened the sense of contradiction. Then came Planck, the European Space Agency's ultra-sensitive observatory, launched in 2009. It was the quiet consummation of a century of cosmological curiosity. Equipped with detectors cooled nearly to absolute zero, Planck was built to capture the oldest light in existence with near-perfect fidelity. As the spacecraft rotated slowly in the silence of space, mapping the microwave sky with exquisite precision, the universe told its story once more, but this time, every detail was magnified. Every irregularity was illuminated. Every anomaly stood in stark relief. The cold spot was real. The Lowell multipole alignments persisted. The hemispherical anisotropy grew more statistically significant. The amplitude of fluctuations on the largest scales remained mysteriously low. The universe, it seemed, carried scars. Scars that did not belong solely to the aftermath of a single explosive beginning, but to something older, deeper, more complex. Planck had confirmed what COBE and WMAP hinted at. The cosmic microwave background was not a perfectly smooth curtain drawn over a singular beginning. It was a textured fabric, woven with threads that suggested inheritance. It was as though the universe was trying, reluctantly, to confess that the story of its birth was not the story of its first moment. While satellites traced the cosmic afterglow, theorists walked their own quiet corridors. In dim offices lit by chalkboards and the soft glow of desk lamps, physicists like Stephen Hawking, Roger Penrose, Alan Guth, James Hartle, and Alexander Vilenkin wrestled with equations that refused to be tamed. Hawking and Penrose broke the mathematical silence first, with singularity theorems suggesting that the universe must begin with an edge, a boundary where space-time collapses. But even their equations hinted that this boundary might not be absolute. It might be a veil rather than a wall. Hartle and Hawking proposed a universe without a boundary, where time gradually transformed into space near the origin, softening the birth of the cosmos into something smoother, less abrupt. Guth's inflationary model explained the uniformity of the universe, but inflation itself hinted at pre-existing quantum fields, structures that could have existed prior to the event that humans call the beginning. Vilenkin's ideas of tunneling from a quantum vacuum opened the possibility of universes emerging not from nothing, but from a metastable timeless state, a cosmic ocean of possibility. None of these ideas provided closure, but they offered something more important, a widening of the horizon, a recognition that the universe's earliest measurable light might contain faint memories of realities preceding it. And as the data grew, as microwave maps deepened and anomalies persisted, suspicion hardened into scientific intrigue. The universe was not giving up its secrets easily. But it was not hiding them perfectly either. It was whispering. The discovery phase of this mystery did not unfold with drama or catastrophe. There were no cosmic ruptures, no flaming skies, no ruptured equations leaking paradoxes into the world. Instead, the truth arrived with humility, a faint hiss of radiation, a series of anomalies drawn across the cosmic background, faint structures that resisted every attempt to erase them. Each data set added weight. Each observation deepened the unease. Each new satellite confirmed what the previous one dared to suggest. The story of the universe was not as simple as a singular beginning. The early cosmos carried traces of something prior, something woven into its symmetry, its temperature, its quantum fluctuations. And all of it entered human consciousness not through explosions or miracles, but through quiet measurements, persistent anomalies, and the patient work of scientists listening carefully to the cold, ancient static of the sky. The universe had begun to speak of its origins. And for the first time, humanity sensed that the Big Bang was not the first word, merely the first word we could hear. In the long corridors of theoretical physics, where blackboards stretch like quiet landscapes and equations hang suspended like constellations, the first tremors of a deeper truth began to ripple through the scientific world. It arrived not in the form of a discovery, but as a contradiction, a fracture in the narrative of origins that humanity had accepted for nearly a century. For generations, the Big Bang had stood as the absolute boundary of time. A singularity, a primordial wall beyond which no mathematics could reach, no hypothesis could venture. a comforting frontier where the laws of physics simply dissolved into silence. But slowly, almost reluctantly, the universe began to reveal that this boundary was not a wall at all. It was a veil. And as this veil thinned, the equations that had once given scientists confidence began to protest. The shock began with the cosmic background itself, the faint afterglow of creation. The anomalies that emerged from Cope, WMAP, and Planck had already unsettled cosmologists, but their implications had not yet fully crystallized. It was only when these irregularities were compared to the mathematical framework of relativity and quantum theory that the full dissonance emerged. The Big Bang, according to classical general relativity, required a singularity, a point of infinite curvature, infinite density, infinite heat, a physical absurdity. Einstein's equations demanded it. Hawking and Penrose proved it. But the data coming from deep space whispered a different story. The universe did not behave like a cosmos with a clean, sharp beginning. There were temperature alignments too orderly for pure randomness. There were fluctuations too large to emerge spontaneously in the first instance. There were hints of earlier structure, faint and haunting, embedded in the oldest light. The first shock was that the Big Bang might not have been a singularity at all. If this were true, then the beginning of the universe was not an origin point, but a transition, a transformation of one state into another, hidden beneath the expanding veil of cosmic inflation. This realization spread through cosmology like a slow, gathering storm. Visual metaphors of the scientific mind changed. The universe was no longer a firestorm erupting from nothingness. Instead, the cosmic camera of imagination drifted into a landscape preceding the bang, a realm where quantum fields churned in timeless fluctuations, where space did not yet stretch, and where the seeds of our cosmos lay dormant like unlit stars. The silence of this pre-bang domain was profound, not empty but filled with the potential for structure, symmetry, and geometry. As cosmologists peered more deeply into the equations of quantum field theory, a second shock emerged. Quantum fields could not be forced into nothingness. Even at zero temperature, even in perfect vacuum, quantum fluctuations persisted. The vacuum seethed with virtual particles blinking in and out of existence, with energy fields that refused to flatten to zero. If this was true, and every experiment in particle physics confirmed it, then the earliest moment of the universe could not have been a perfect reset. Something must have carried through. A memory, a condition, a structure that predated the expansion. This insight collided violently with the traditional model of cosmology. A universe that inherits conditions from a prior state implied a greater continuity, perhaps even a cyclical or multi-phased cosmic history. The very fabric of the cosmos seemed to remember. The intellectual earthquake intensified when scientists turned to inflation theory, the exponential stretching of spacetime in the first fraction of a second. Alan Goose's elegant model had long been celebrated for explaining the smoothness and uniformity of the universe. But inflation came with its own demands. Inflation required a driving field, the inflaton, with a specific, finely tuned potential. And more importantly, inflation required initial conditions that were already smooth over horizon-scale regions before the expansion began. In other words, inflation itself hinted that something existed before inflation, something that set the stage, prepared the fields, aligned the geometry. The early universe appeared less like a chaotic eruption and more like a cosmic transition with preparation hidden behind the curtain. This was the third shock. Inflation could not erase all traces of what came before. No matter how violently spacetime expanded, no matter how drastically the universe smoothed its own wrinkles, certain patterns persisted. The low multipole anomalies, the hemispherical asymmetry, the cold spot. These were like faint fossils in the cosmic sand, impossible to remove. If these features came from pre-inflationary physics, then the Big Bang was not the beginning, but merely the boundary of visibility. The most profound shock came when physicists confronted entropy, the measure of disorder. According to thermodynamics, the universe should have begun in an extraordinarily low entropy state. But no natural mechanism could explain why a universe emerging from nothing would begin so improbably ordered. Roger Penrose called this the extraordinary fine-tuning problem, A mystery so severe that it seemed to demand a universe before the universe, a cosmic cycle, a previous contraction, or a pre-existing geometric state. Entropy, more than any other concept, shook the intellectual foundations. The equations described a young universe that was too clean, too uniform, too impossibly pristine, as though it had passed through a filter before being allowed to expand. This was the fourth great shock. The universe appeared prepared, not designed, not guided, but conditioned by events prior to the Big Bang. In the theoretical wings, quiet battles unfolded. Relativity insisted that time had a beginning. Quantum mechanics insisted that fluctuations were eternal. Inflation insisted that something ceded its potential. Entropy insisted that order must be inherited. The equations contradicted one another like ancient texts written in different languages, each describing a truth but none offering the whole story. Physicists found themselves trapped between worlds. A universe that must begin, but could not have begun absolutely. A universe that must emerge from nothing, but could not be born from true emptiness. A universe whose earliest moments were smoothed, but not erased. This conflict produced a deep emotional weight, a questioning that extended beyond formulas and graphs. Scientists had long taken comfort in the notion that time began at t=0. There was safety in a boundary, a sense of closure, a cosmic bookend. But now that bookend was dissolving, the emotional shock spread quietly through lecture halls and research institutes. In the stillness of offices cluttered with manuscripts, scientists found themselves staring at diagrams of the early universe with a sense of disorientation, as though the ground beneath physics had subtly shifted. Some felt excitement, a horizon newly opened. Others felt unease, the known laws no longer enough. All felt the gravity of the moment, a realization that the universe was not the simple story they had long believed. The scientific community has experienced shocks before. The revelation that Earth is not the center of the universe, the understanding that galaxies recede in all directions, the discovery of dark matter's invisible scaffolding, the acceleration of cosmic expansion attributed to dark energy. But this shock was deeper, older, more intimate. It struck at the origin of reality itself. As the new century unfolded, the idea that the universe inherited properties from an earlier state moved from fringe speculation to serious scientific debate. Loop quantum cosmology suggested a bounce, a contraction leading into an expansion. Eternal inflation described a multiverse where universes continuously bud from inflating fields. The Hartle-Hawking model replaced a beginning with a smooth transition from spatial geometry. None of these theories offered final answers. But they shared one theme. The universe did not begin with absolute nothingness. It transitioned from a state beyond classical comprehension, a timeless region where quantum geometry ruled, where fields shimmered without space, and where the seeds of our cosmos were already stirring. This realization was not merely scientific, it was philosophical, a reconfiguration of humanity's place within the cosmic narrative. The once stable idea of a single beginning was dissolving. In its place emerged a universe connected to something older, perhaps infinite in depth, perhaps cycling endlessly, perhaps part of a far grander architecture than human thought had dared to imagine. And so the scientific shock deepened, not as a moment of discovery, but as a slow, unfolding recognition that everything once believed about the origin of time was incomplete. The universe had revealed only its first layer. Behind it, another waited, older, stranger, and still veiled in the quiet light of the cosmic dawn, in the quiet afterglow of the universe's first light. The cosmic microwave background drifts like ancient dust, an echo from an age when the cosmos was barely old enough to know itself. For decades, scientists treated it as a sacred map, a perfect record of the Big Bang, frozen across the sky. Its faint ripples were the universe's earliest memories, imprinted long before galaxies, stars, or planets had names. But as instruments sharpened and theories matured, patterns once dismissed as noise began whispering of deeper fractures. Subtle distortions in curvature, temperature anomalies far too large for standard inflation, a cold region carved into the sky like an absence, a void so improbable it strained the mathematics that once explained everything. The deeper humanity looked, the more the ancient map seemed to fold, twist, and recoil from our expectations. Conflicting satellite missions offered competing versions of the same cosmic story. Quantum simulations hinted at structures predating expansion itself. And in the faintest tremors, physicists detected the ghostly possibility of waves, gravitational murmurs, passing through the universe from a time before time. This chapter is where the descent begins. Not into chaos, but into the darker waters of understanding, where light bends, assumptions fracture, and every answer reveals something older, stranger, and far less obedient to the laws we once believed complete. Here, the universe no longer behaves like a clean beginning. It behaves like a palimpsest, its earliest pages overwritten, bearing scars from events that should not exist. And the deeper one goes, the more the universe feels less like an explosion, and more like an inheritance from something hidden beneath. The camera drifts slowly across the primordial sky, suspended in the soft radiation that fills all of space. The cosmic microwave background glows before us like a fog of ancient embers, annotated with the earliest geometry of existence. Against this tapestry, the journey inward begins, not upward toward stars, nor outward toward galaxies, but downward into the mathematics behind what they imply. Scientists once believed this background to be nearly perfect, a uniform field of temperature with only the faintest ripples, just enough to seed galaxies billions of years later. But perfection has a way of crumbling under scrutiny. As satellite missions refine their gaze, from COBE to WMAP to Planck, the supposedly featureless ancient sky began revealing fingerprints of a subtler, more unsettling story. The narration slows, as if the universe itself exhales. The curvature data came first. Tiny deviations, mere whispers, where theory predicted silence. The geometry of the early universe appeared to lean, ever so slightly, away from the smoothness promised by simple inflation. Lines that should have been straight were gently arched. Symmetries that should have been unbroken showed a faint, persistent tilt. Individually, they were statistical curiosities. Together, they hinted at an early cosmos warped not by chance, but by something older than the expansion that followed. Then came the cold spot. The camera sinks into it, a vast, silent continent of lowered temperature, carved into the microwave sky like a shadow cast by something no longer present. Too wide, too deep, too structured. Traditional models could not generate such a void without invoking improbability so staggering that it undermined the very statistical foundations of cosmology. Some proposed that a supervoid, a colossal region nearly empty of galaxies, might lie along our line of sight. But surveys found no such structure large enough to account for the anomaly. Others suggested that quantum fluctuations during inflation may have left an unusually large imprint. Yet the mathematics struggled to justify its scale. The cold spot persisted like an impossibility embedded in the sky, in ancient silence colder and darker than theory permitted. Conflicts emerged. WMAP data hinted at one interpretation, Planck at another. Each mission measured the same cosmos, yet extracted different fingerprints. Their discrepancies fueled debates that split cosmological models into branching, competing realities. Inflation theories multiplied: simple inflation, chaotic inflation, eternal inflation, hybrid models, multi-field models, loop corrections, energy landscapes drawn across higher dimensional fields. Every version tried to explain a universe increasingly unwilling to behave. With each new dataset, cosmology felt less like a completed textbook and more like a fracturing manuscript, pages rewritten by observations that resisted coherence. The camera descends deeper. In the realm of quantum foam simulations, the domain where space itself flickers between possibilities, the anomalies sharpened. Models attempting to recreate the earliest moments of the universe generated structures that should not survive beyond the Planck epoch. Yet some simulations produced repeating features reminiscent of the anomalies seen in the cosmic background, patterns echoing through time as if remnants of a pre-expansion architecture. These were not stars. They were not particles. They were not even physical in any way a human mind could hold. They were scars. Scars from a state older than space-time, scratches left on the universe by whatever existed before the Big Bang's inflation smoothed the cosmos into near uniformity. And though inflation should have erased them, faint shadows remained, like the ghost of a deeper geometry refusing to vanish. The camera now reveals another layer. Hints of gravitational waves, soft, elusive tremors, appeared in the data. Not the waves generated by merging black holes, but frequencies far older. Their wavelengths were too large, too ancient, and too faint to belong to the later universe. Some researchers speculated they might be pre-inflationary, remnants of a cosmic epoch before expansions stretched them beyond detection. If true, they were not simply waves. They were memories. Memories from a time before the cosmos expanded, before space cooled, before the laws of physics crystallized into their current forms. These waves would have passed through whatever came before, brushing the surface of the newborn universe, leaving behind slight asymmetries that billions of years later we now interpret as anomalies. But such ideas were controversial. Academic halls erupted into philosophical wars. Inflationists clung to the elegant simplicity of the established model, insisting that most anomalies lay within acceptable statistical variance. Others argued that contradictions were accumulating faster than resolutions. New theories sprouted along the boundary between physics and metaphysics, suggesting that the Big Bang may not have been a beginning, but a transition, a collapse from an earlier universe, a bounce from a previous contraction, a fracture in a higher dimensional space, a phase shift in a field older than spacetime. Each theory offered answers while exposing deeper ignorance. The narration slows, mirroring the descent into uncertainty. The camera moves into the cold spot once more, downward, as if falling through layers of ancient echoes. Surrounding it, the familiar fluctuations of the cosmic background shimmer like soft rainfall. But within the cold region, the texture changes. It becomes less random, less innocent. Patterns faintly align. Temperature variations curve toward a subtle axis, an axis not predicted by standard cosmology. This alignment is the quiet heart of the mystery, a possible imprint of another universe, a bubble collision in a multiversal sea, a remnant of a pre-Big Bang structure pressing against our own cosmos. None of these interpretations are proven, but none can be dismissed. As the camera pulls back, the microwave sky reappears, an ocean of faint color, speckled with the ripples of primordial sound waves. To the untrained eye, it is beautiful. To the trained one, it is fractured, ancient, tired. Evidence deepens, but clarity does not. Answers multiply, but certainty dissolves. Humanity's descent into the data reveals not a single narrative, but a labyrinth, not a beginning, but a boundary. Each anomaly feels like a doorway, leading not outward, but inward, toward a deeper strangeness underlying the cosmos. And as the final shot drifts through the cold spot one last time, the universe feels less like an explosion into emptiness, and more like a surface stretched thin over something waiting beneath. There comes a moment in every investigation when the trail no longer leads outward, but downward, into places where the familiar dissolves and the foundations beneath begin to tremble. In cosmology, that moment arrives when the evidence suggests the universe may not have been the first stage of reality, but merely a chapter in a much older manuscript. The early anomalies were curiosities. The deeper ones were warnings. But together, they began to outline something more dangerous, a breach in the idea that the cosmos has a singular beginning. If the universe inherited structures rather than created them, then the laws governing existence are themselves descendants, passed down from a state predating spacetime. And if time had a history before the Big Bang, then its earlier form may have operated under different rules, unconstrained by causality, continuity, or direction. Einstein's boundary conditions, long thought to seal the universe at its origin, begin to fray. Hawking's no-boundary proposal, once elegant in its closure, starts to feel too compact for the growing strangeness of the data. And inflation, the grand architect smoothing chaos into cosmos, fractures into a forest of models, each claiming a different prelude to creation. Here, cosmology does not merely search for answers. It confronts its own fragility. the mystery darkens into something existential, that the universe humans inhabit may not be fundamental at all, but derivative, an offspring of a deeper realm, sculpted by forces without name or precedent. And in this chapter, the camera enters the widening fault line, where familiar physics gives way to inherited physics, and where creation itself begins to look less like a beginning, and more like a continuation. The camera drifts through the dim afterglow of the cosmic microwave background, its faint light stretching across the sky like the bruised memory of an ancient event. The anomalies uncovered in earlier investigations linger like fractures beneath a veneer of order. But in this chapter, the view shifts, pulling back from isolated puzzles and revealing the shape they form when seen together. A shape that implies the universe carries scars, not from its birth, but from something before it. Slowly, the frame transitions into a deep, structureless darkness, an interstellar void untouched by stars, galaxies, or dust. Here, the narration deepens. The void becomes a metaphor, a boundary where explanations fail, where physics is forced to confront what it has long feared to ask. For nearly a century, the Big Bang stood as a cosmic genesis, an absolute beginning not merely in time, but in meaning. Everything, space, laws, forces, constants, was believed to emerge from the same moment of creation, unified by a single birth event. According to Einstein's equations, the universe could be traced backward until space-time curved into a singular boundary and ceased. But anomalies do not obey philosophical comfort. The cold spot, the curvature deviations, the gravitational murmurs older than expansion, the persistence of unexplained alignments across the microwave sky. Individually, each strained the standard model. Together, they whispered of inheritance, features too large, too intentional, or too ancient to have arisen within the few billionths of a second after the Big Bang. They hinted that the Big Bang may not have been a beginning at all, but a transition. The camera now sinks through a vast nebula, its clouds glowing with hydrogen fire, dust swirling like luminous smoke. The visual contrast is intentional, creation emerging from collapse, structure rising from remnants. It mirrors the possibility now haunting cosmology, that this universe may be built from the debris of something older. If this is true, then the laws of physics themselves are not fundamental. They are inherited. Physical constants, once treated as sacred, begin to look like imprints of earlier conditions. The strengths of forces, the mass of particles, the behavior of quantum fields, all may be second-generation traits, not universal inevitabilities, but relics of a prior cosmic environment. The narration grows quieter, more contemplative. If time existed before the Big Bang, it may not have behaved like time. Not as a flowing sequence, not as an arrow, not as a path. It may have been a dimension without direction, a landscape rather than a river. The notion fractures the deepest assumptions in physics, that causality is absolute, that events must follow one another, that the universe unfolds from past to future. In pre-Big Bang models, loop quantum cosmology, ekpyrotic cycles, bouncing universes, time compresses, twists, or folds. It becomes nonlinear, irregular, something closer to a potential than a progression. The camera descends into the gravitational well of a supermassive black hole, its event horizon stretching like the lip of a cosmic waterfall. Frame by frame, space-time distorts. It is a visual metaphor for what happens to physics when time loses meaning. At the event horizon, time slows. Beneath it, time may not exist at all. This imagery reflects the crisis unfolding in cosmology. Einstein's boundary conditions rely on the assumption that space-time must begin at a singular point. Hawking's no-boundary proposal treats this beginning not as a physical edge, but as a smooth closure, where time transitions into space in a manner that avoids singularity altogether. But both depend on the universe having no before. When evidence suggests inheritance, these boundary conditions crumble. Not because Einstein or Hawking were wrong, but because the universe may be older, deeper, and less singular than the equations once implied. The inflationary model, the engine driving the universe's early exponential expansion, was designed to erase all traces of pre-Big Bang features. Yet traces remain. Too many. Too consistent. As anomalies accumulate, inflation fractures into competing interpretations. Some versions suggest the cosmos expanded from a quantum vacuum. Others propose that inflation occurs eternally, generating bubble universes in an ever-growing multiversal sea. Some models require predecessors, others ignite spontaneously. No two agree completely. And the more models appear, the more the theory loses its inevitability. The camera sweeps into an infinite fractal of bubbles, soft glowing spheres suspended in darkness, like lanterns floating across a cosmic ocean. Each bubble wavers with its own physics, its own constants, its own geometry. This is inflation's most radical implication, a multiverse not as speculation, but as requirement. If our universe had a before, then it belongs to a lineage. And if it belongs to a lineage, then it is not alone. The emotional tension deepens, not fear, but a profound sense of displacement. The idea that humanity lives in a universe that is derivative, not fundamental, challenges the desire for cosmic singularity. It reframes existence from absolute origin to inherited continuation. The narration becomes philosophical, though still grounded in science. If the universe is not the first, then what came before is not simply older, it is foundational. It shaped the laws, seeded the geometry, influenced the behavior of fields. The universe becomes the echo, not the shout. The artifact, not the author. This shift destabilizes cosmology because it challenges the purpose of the field itself. Instead of explaining the universe, cosmology must now explain its ancestry. The camera drifts into a dark region where no stars burn, an interuniversal void, imagined yet consistent with the mathematics. Here, subtle ripples distort the darkness, representing gravitational signatures that might arise from earlier cycles. In this space, the narration reflects on what remains unresolved. What mechanism allowed a previous cosmos to seed ours? Did an earlier universe collapse into a bounce? Did it tunnel through a higher dimensional landscape? Did it fragment into many futures? Or did it decay, leaving only the faintest imprints carried into the next reality? Each question fractures the boundaries of contemporary physics. Every answer suggests deeper origins. The chapter reaches its meditative climax as the camera returns to the cosmic microwave background. The cold spot lingers like an ancient bruise. The alignments stretch across the sky like scars. The curvature anomalies shimmer with quiet defiance. Together, they outline a single implication. The universe humans inhabit is not fundamental. It is derivative. It is inherited. It is the child of something older. The narration softens into final reflection. If the cosmos is not the first, then existence stretches beyond the horizon of imagination, not as a singular event, but as a chain of realities, each bequeathing its traits to the next. And the mystery deepens not because the universe is unfinished, but because it is unrooted. In the quiet margins where theory stretches beyond observation, the universe reveals itself not through certainty, but through possibility. Here, in a realm without telescopes or edges, physicists sketch the shapes of realities that may have preceded our own. The camera drifts through interstellar dusk, across nebulae swollen like embryonic clouds, as if the cosmos is trying to remember the circumstances of its own birth. Each theory glimmers like a distant lantern, its light faint, its origin unknowable, yet each attempts to describe what existed when time itself was only beginning to take form. Some models imagine the universe collapsing into a density too immense to name, only to rebound, breathing again in a rhythmic cycle older than memory. Others propose that the beginning was not a moment, but a boundary, smooth and rounded like a stone polished by eternity, where time blurred gently into space until neither could be distinguished. Still others paint a restless cosmic sea, an infinite, ever-inflating vacuum spawning islands of space-time like foam, each universe a temporary spark in a storm without end. These ideas are not fantasies. They are mathematical shadows, projections cast by general relativity, quantum gravity, string theory, and the desperate need to reconcile what cannot be reconciled. Yet every answer opens a deeper silence. Every explanation leaves a new darkness unexplored. In this chapter, the The theories gather like quiet voices around the same unsolvable riddle. If our universe was born from something older, what was that something? A bounce? A collision? A quantum fluctuation? Or a realm so different from our own that words like before and after no longer apply? The journey now enters the landscape of cosmic imagination, where science meets the edges of existence itself. The camera glides through the interstellar void, passing drifting clouds of ionized gas, the faint blue ghost light of ancient stars, and the quiet structures carved by long-vanished winds. In this vast silence, the universe becomes a canvas for speculation, a place where mathematics, philosophy, and cosmology converge to ask the most delicate of questions. What lies on the far side of the beginning? 1. Loop quantum cosmology, the universe that breathes. The descent begins in a realm woven not from classical space-time, but from discrete quantum threads. Loop quantum cosmology, LQC, proposes that space is not continuous, but granular, made of tiny loops so small they defy direct observation. When folded into the early universe, these loops resist the infinite collapse predicted by general relativity. As matter compresses and density mounts, quantum geometry stiffens, halting the plunge into a singularity. Instead of an infinite point, the universe hits a boundary of quantum pressure and rebounds. A contraction becomes an expansion. A dying cosmos becomes a newborn one. The Big Bang becomes a big bounce. The camera descends toward a simulated singularity, which softens into a luminous quantum weave, oscillating like a cosmic lung. This universe does not begin, it transitions. Each cycle inherits subtle conditions from the previous one: curvature, anisotropy, energy distributions. But LQC cannot yet explain the origin of the cycles, nor why one emerged instead of another. It replaces the singularity, but leaves the deeper question intact. Why does anything bounce at all? 2. The Hartle-Hawking no-boundary proposal, a universe without an edge. The scene shifts, stars fade, and the screen fills with a mathematical horizon where time curves like a wave slipping into still water. Stephen Hawking and James Hartle proposed that the universe did not erupt into being. Instead, the beginning resembled a smooth turning of dimensions. Time, at extreme energies, may behave like space. Instead of a sharp beginning, the cosmos transitions from a timeless realm into a temporal one, as gently as dawn rising over a dark ocean. No singularity, no edge, just a gradual emergence. In this model, the early universe is finite but unbounded, like the surface of a sphere, which has no center and no edge, yet contains all its points. Time becomes a direction only after a certain threshold is crossed, like a dimension crystallizing out of quantum mist. But the model struggles to predict the precise conditions needed for inflation, and competing interpretations debate whether the no-boundary condition is physically realizable. It offers elegance, but its mathematical footing rests on complex path integrals still not fully understood. 3. Eternal inflation, the infinite storm. The camera plunges into an ocean of quantum energy, roaring, violent, unending. Inflation, originally proposed to explain the cosmos' smoothness and uniformity, evolves here into something more sweeping. In some versions, inflation never ends globally. It stops only locally, forming bubble universes that cool into distinct realities. Our universe becomes a single bubble drifting among countless others, each born from the same inflating field but shaped by different quantum accidents. Some bubbles expand with different physics. Some collapse immediately. Some may carry dimensions inaccessible to ours. This is the multiverse not as metaphor, but as mathematical consequence. The camera reveals an infinite foam, each bubble a universe expanding silently into the inflating sea. Within our bubble, the Big Bang is not a beginning. It is a boundary between inflation and post-inflation. Beyond it lies an eternally expanding field, endlessly spawning new universes. The model explains certain cosmic anomalies and fits well with high-energy field theory. But it has deep flaws. It predicts too many possibilities, making specific predictions nearly impossible. And worse, it threatens to render explanation meaningless. If everything happens somewhere, nothing can be disproven. For ekpyrotic and cyclic universes, the colliding brains. The tone deepens. The camera drifts through a higher dimensional space, vast, silent, shadowed. Here, our universe is not alone but lives on a membrane, brain, suspended in a higher dimensional arena. Occasionally, these brains collide, releasing enormous energy and birthing a new cosmos. In the ekpyrotic and cyclic models, the Big Bang is not an explosion from nothing, but the aftermath of a colossal impact between cosmic sheets drifting through a multi-dimensional expanse. With each collision, entropy resets, expansion begins anew, cosmic history unfolds again. The camera visualizes two shimmering membranes approaching in slow cosmic motion, then touching, igniting a firestorm of new physics. These models elegantly avoid singularities and can reproduce many features of the cosmic microwave background, but they require dimensions we cannot yet test and rely on string theory's vast mathematical architecture, a structure still unverified by experiment. 5. Quantum vacuum emergence, a universe from a timeless sea. The journey now enters the most abstract territory. The camera reveals a dark, shifting field, neither emptiness nor somethingness. It is the quantum vacuum, a substrate where particles and fields arise and vanish spontaneously. Here, the universe could emerge not from a previous cosmos, but from the inherent fluctuations of this underlying quantum state. The Big Bang becomes a quantum event, an improbable but not forbidden transition, like a spark leaping from a cold stone. This idea draws upon quantum tunneling, vacuum metastability, and the mathematics of false vacuum decay. In some scenarios, the universe tunnels from a timeless state into inflation, producing space-time as a byproduct of the transition. But this raises profound questions. If the vacuum is timeless, what does transition even mean? If time emerges only after the event, what governs the event itself? The theory offers a framework but leaves the origin of the vacuum unexplained, a silence beneath the silence. The beauty and the failures. The camera pulls back, revealing all theories as if suspended in space, glowing diagrams drifting like constellations of intellect. Each illuminates some corner of the mystery. None illuminate all of it. Loop quantum cosmology solves the singularity but not the cycles. No boundary removes the beginning but blurs the initial conditions. Eternal inflation explains the structure but erases predictability. Ekpyrotic models replace creation with collision but rely on untested dimensions. Quantum vacuum emergence explains the transition but not the substrate itself. Every model reaches for truth. Every model grasps only a fraction. The universe remains partially veiled, as if protecting the deepest chapter of its autobiography. And so, the search continues, toward horizons where mathematics trembles, where philosophy becomes necessary, and where the cosmos whispers that even its beginning may only be a beginning of something far older. That in the vast silence that surrounds all things, the universe offers almost nothing freely. Its deepest truths lie buried beneath horizons of time, wrapped in temperatures near absolute zero, encoded in radiation older than galaxies. Most of what existed before the first stars has been erased, stretched, blurred, and scattered across a cosmos still expanding from a beginning no one witnessed. Yet, across a small blue world orbiting an ordinary star, a species continues to build devices meant to pry open that silence, machines that do not merely observe the universe, but interrogate it. Here, in the forests of Chile and the deserts of Antarctica, in orbits far beyond the moon, in cryogenic underground corridors where particles whisper through magnetic labyrinths, humanity constructs its lanterns, not to conquer the darkness, but to understand it. Each instrument listens for vibrations older than light itself. Each mirror and detector searches for the relics of a vanished age, patterns older than inflation, ripples seeded before the Big Bang, signatures of dimensions the universe no longer reveals. These tools are fragile, finite, painfully human. Yet through them the cosmos speaks. And as the camera drifts across Earth's night side, cities glowing like constellations made by restless hands, another truth emerges. humanity has begun turning its most powerful technologies toward a question older than time. Not how the universe began, but whether it ever truly did. This is the story of our greatest scientific instruments, and the ancient echoes they hope to catch before they fade forever. Humanity's lanterns in the primordial dark. Across the silent reaches of the universe, the oldest memories of reality drift faintly, like dust suspended in an endless night. Most are almost gone, smoothed by cosmic expansion, diluted by entropy, buried beneath eons of starlight. Yet the scientific mind refuses to surrender them. It builds tools of extraordinary precision, reaching backward through time, searching for the fingerprints of a world older than the universe itself. The camera glides through the frozen vacuum above Earth, approaching a distant golden mirror that glints softly in the sun. The James Webb Space Telescope, humanity's current sentinel of the cosmic dawn. 1. WST, the mirror that hunts the first light. Webb stares not at stars as they are, but as they were when the universe was only a few 100 million years old, an age so remote that light has been stretched into infrared whispers. Its instruments sift through this ancient glow, seeking anomalies that should not be there, galaxies forming too early, stars too massive, voids too deep. For cosmologists, these are not mere curiosities. They are possible clues, hints that the first structures were shaped by conditions preceding the Big Bang. If the universe experienced a contraction before rebounding, echoes of that phase might appear in WST's deep field mosaics. Unusual clustering, deviations from standard inflation, signatures of a geometry once compressed beyond imaginable density. The telescope's golden petals drift in reflective silence, gathering photons that began their journey before the Milky Way existed. Through it, humanity asks the cosmos a question it cannot phrase aloud. What happened before light was born? 2. The Simons Observatory and CMBS-4, listening to the universe's oldest breath. From the high deserts of the Atacama, vast dish-shaped detectors tilt toward the sky. Their task is deceptively simple. Measure the temperature of the cosmic microwave background with sensitivity nearly beyond comprehension. But hidden in that faint afterglow may lie the universe's oldest scars. The Simons Observatory and the forthcoming CMB-S4 project hunt for primordial gravitational waves, ripples in spacetime generated in the first trillionth of a second. If detected, these waves could confirm or challenge inflation, reveal cracks in spacetime geometry, or even hint that our universe once contracted before expanding again. As the instruments sweep the heavens, the camera drifts across their frozen surfaces. Frost glitters like starlight. Each detector sits at the edge of human engineering, chilled nearly to absolute zero, listening to radiation only a few degrees above perfect darkness. Scientists hope these vibrations will reveal patterns impossible to produce by the Big Bang alone. Patterns suggesting a universe that oscillates, bounces, or inherits features from dimensions that no longer exist. In these chilled deserts, amid the silence of ancient plateaus, humanity listens for echoes older than time. 3. Space-based gravitational wave observatories, LISA and the Big Bang Observer. Far from Earth, in orbits synchronized across millions of kilometers, 3 spacecraft drift in a perfect triangular formation. This is LISA, the Laser Interferometer Space Antenna, designed to detect gravitational waves too slow, too deep, too ancient for ground-based detectors to hear. Where Earth-based instruments catch the violent collisions of black holes, LISA and the proposed Big Bang Observer aim for something far quieter, the faint, primordial hum produced before the universe became transparent to light. These signals are relic vibrations of the primordial era, tremors from symmetry breaking, vacuum shifts, or cosmic phase transitions preceding the first atoms. If these spaceborne observatories hear the right patterns, if they detect specific spectral imprints, then the universe's earliest moments may reveal themselves not through light, but through rhythm. The camera moves through their laser paths like drifting through strands of cosmic silk, each beam measuring distortions smaller than a proton's width. In that precision lies possibility, a way to see before sight itself, to hear before there was light. For particle colliders, searching for the structure beneath reality. Deep beneath mountains and countryside, particle accelerators form glowing rings of magnetized steel. Here, humanity probes the quantum vacuum, the stage on which all laws of physics perform. If the vacuum possesses hidden structure, if it retains memory of a prior universe, or if its symmetries once fractured in ways no longer visible, then particle collisions are the tools to reveal it. At energies pushing the limits of technology, protons collide and splinter into fountains of subatomic debris. Detectors capture the traces, spirals, arcs, and cascades of particles that last for millionths of a second. These collisions test ideas older than modern cosmology. Did the universe tunnel into existence from a prior vacuum state? Were extra dimensions compacted in the first fractions of time? Do the forces of nature hint at a history before the singularity? Each experiment is an interrogation of the void itself, an attempt to ask whether emptiness is truly empty or simply hiding its past. 5. Quantum sensors, the next frontier of precision. In labs shielded from noise, vibration, and even the Earth's magnetic heartbeat, quantum sensors hover in delicate balance. They measure fluctuations in space-time with sensitivity unimaginable a generation ago. Some detect ultralight fields that could be remnants of pre-inflation physics. Others search for violations of symmetry, minute imbalances hinting that the universe inherited an asymmetry from a previous phase. These devices are the smallest lanterns ever built, fragile, silent, impossibly precise. And yet they may reveal the largest mysteries, because the earliest moments of the universe were governed not by stars or galaxies, but by the quantum rules these sensors probe. Through them, humanity examines the fabric of reality not by sight or sound, but by the trembling of atoms. 6. The purpose behind the machines. Though each instrument is different, their mission converges. To determine whether the universe's beginning was absolute, or merely a transition, scientists search for patterns older than inflation, textures inconsistent with a singular origin, residual imprints of a contraction phase, vibrational modes from forgotten dimensions, anomalies in vacuum structure, unusual clustering in early galaxies. Each would be a clue, a fingerprint left by a cosmos older than its own birth. And yet, there is humility in this pursuit. Every instrument acknowledges a limit. The universe has erased most of its past, but not all of it. 7. Humanity's lanterns against an infinite night. The chapter's camera draws back from Earth, rising above observatories, accelerators, and telescopes that glow faintly against the turning globe. From this height, humanity's entire scientific infrastructure looks impossibly small, a scatter of glimmers beneath an ocean of stars. Yet these glimmers hold meaning. They are attempts to reach into an age no living thing has ever seen. Attempts to illuminate a darkness older than galaxies, older than atoms, older than time as we perceive it. Whether these tools will succeed is unknown, but their existence alone tells a quiet, profound truth. The universe may guard its origins fiercely, but humanity is learning to build light. Light precise enough to read the afterimage of creation. Light sensitive enough to detect the faint breath of a world before this one. Light brave enough to confront the possibility that the cosmos had no beginning at all. The chapter ends as the camera drifts into interstellar darkness, leaving Earth a distant glint behind. Ahead lies the void, vast, silent, ancient. And somewhere within that darkness, the first secrets of existence still wait, buried beneath the unfolding light of human curiosity. Across the endless dark, where galaxies drift like embers scattered from an invisible fire, there exists a silence older than any star. It is a silence deeper than the cosmic void, untouched by atoms, unbroken by radiation, unmarked by time. It is the silence from which the universe emerged, and the silence into which all things will eventually fall. But that silence may not be emptiness. It may be memory. As the camera floats through a cathedral of interstellar dust, the faint glow of distant nebulae paints the darkness in soft hues: rose, gold, indigo. Every color is ancient. Every photon carries the story of something that once was. If the universe is not a beginning but a continuation, then this silence may hold the remnants of worlds long forgotten. It may be the echo of cycles beyond imagination, cosmic epochs in which universes bloom, collapse, and bloom again, each inheriting the quiet scars of the one before. In this chapter, the film drifts gently toward the idea that existence itself may be a continuum, a great cosmic breath drawn and released across unimaginable ages. A rhythm so vast that stars themselves are brief flickers within it. And somewhere within that rhythm, hidden in the faint background glow, in the geometry of space-time, in the fragile spark of consciousness, lies a question that has haunted humanity since the first mind looked upward. If the universe is part of a cycle, then what, exactly, is being carried forward? And why does it feel like we are only now learning to listen? A slow return to the primordial hush. As the chapter opens, the cosmos stretches outward in a great, quiet expanse. Galaxies drift like frozen waves on a black ocean, each one a swirling storm of stars. But the camera begins to withdraw, from the spiraling arms, from the luminous cores, from the glittering halos of dark matter, until even the largest clusters fade into a lattice of faint light. From this distance, the universe resembles a single breath. A single shimmering inhalation suspended in time. And the narration turns toward the oldest question of all. What if this breath is not the first? For generations, cosmology treated the Big Bang as an absolute beginning, a singular moment when all laws, particles, and energy emerged from nothing. But as scientific imagination expands, a new idea quietly rises in the background of physics. The universe may not be the opening note of creation. It may be a continuation of something far older. 1. The continuum of existence. Across cosmic cycles, entropy rises, structures collapse, horizons fade. Yet the universe seems to resist finality. Some mechanism, some law, some deep symmetry, appears to preserve the possibility of rebirth. Loop cosmology suggests a bounce. String cosmology imagines collisions of higher dimensional brains. Inflationary models propose eternal budding universes in an infinite foam. Different languages, different physics, but all whisper the same idea. This is not the first universe, and perhaps not the last. If reality is cyclic, then every galaxy ever born is part of a lineage. Every atom is a descendant of universes that no longer exist. Every mind carries echoes of physical laws refined across unfathomable epochs. The camera drifts through the remnants of a supernova, dust cascading like shimmering ash, and the narration wonders if even the forces that govern collapse and renewal might themselves be inherited from universes gone dark. 2. The meaning of origins without a beginning. Without a singular beginning, the human idea of origin dissolves. Time becomes a river without a spring. Existence becomes a tapestry with no first thread. This idea does not diminish the universe's majesty, it magnifies it. It sets humanity not at the start of creation, but at the midpoint of an eternal process. A participant in something far larger, older, and more intricate than imagination alone could conceive. Suddenly, the Milky Way is not an isolated miracle. It is a chapter, a brief, luminous paragraph in a book that has no first page. 3. Consciousness in a cyclic cosmos. As the camera drifts toward a glowing blue world, Earth floating quietly in shadow, a new question arises. If universes cycle, then what of consciousness itself? Is it an accident of chemistry? A fleeting spark in the darkness? Or is it an inevitable expression of cosmic evolution? Some physicists speculate that conscious observers play a role in interpreting or stabilizing quantum histories. Others explore the possibility that life's emergence is intertwined with the universe's deep symmetries. The narration does not claim answers, only possibilities. Consciousness may arise wherever the cosmos becomes complex enough to observe itself. It may be the universe learning to see. It may be part of the cycle. Just as gravity sculpts galaxies, consciousness may sculpt meaning. Just as stars illuminate space, minds illuminate understanding. And if universes succeed one another, the capacity for awareness might not be an anomaly, It might be a recurring phenomenon woven into the structure of space-time. The camera glides past the curvature of Earth, cities glowing like constellations stitched into the night. Amid this fragile light, humanity becomes more than biological. It becomes cosmic, for the weight of knowing. If the universe is cyclic, if countless realities have come and gone, then a profound shift occurs in humanity's place within existence. We are not witnesses to the first dawn. We are participants in an ongoing story. In a cyclic cosmos, the pursuit of knowledge becomes more than curiosity. It becomes continuity, a transmission across ages. Every discovery is a message carried forward. Every insight is a bridge between cycles. Every scientific instrument is a lantern held up against an ancient night. The chapter shows Earth from a great distance, a faint glimmer in an ocean of darkness. Thin, fragile, beautiful. And then, softly, the narration reflects. Perhaps meaning does not come from being the first. Perhaps meaning comes from being part of an unbroken chain. The camera now leaves the Milky Way entirely, rising into intergalactic night. Stars recede into a faint mist. Time feels slower, colder, more ancient. This is the primordial hush, the silence that existed before the first light. A silence not of nothingness, but of waiting. Waiting for geometry. Waiting for energy. Waiting for the moment when existence would ignite again. And as the film drifts deeper into that quiet, the final reflection emerges. Before the first star burned, before the first atom formed, before time chose a direction, something existed. Something timeless. Something patient, something that may still echo faintly in the background of reality. Humanity is only now beginning to hear that echo, through telescopes, through gravitational instruments, through theories that dare to extend beyond the horizon of creation itself. The chapter closes with a final, gentle truth. The universe is not silent. It is whispering, and we are finally learning to listen. As the last stars fade and the screen dissolves into darkness, a final reflection drifts across the quiet. The cosmos is vast, its cycles ancient, its mysteries endless, and the journey to understand them has only just begun. If this exploration moved you, if you felt the echoes of something older than time, consider supporting this voyage into the unknown. Subscribe to Science Scroll. Like the video, share the wonder, because the universe is still whispering. And together, we can follow its voice into the next chapter of discovery. A slow, cinematic descent into the primordial dark, before light, before space, before the first trembling second of time. The chapter opens in a realm without direction, without form, without the mercy of dimensions. A place where temperature, entropy, and causality have no meaning. A silent ocean of potential, folded into itself like a universe waiting to inhale for the first time. Describe the pre-time hush as an almost sentient quiet, a cosmic stillness dense enough to bend thought, delicate enough to feel like it might shatter if touched. Introduce the central mystery, that the Big Bang was not the beginning, but the echo of something older. Something stranger. Something that left fingerprints in the very fabric of space-time. In gravitational waves, cosmic background radiation, quantum fields trembling at the edge of nothingness. End with a chilling suggestion that the universe did not begin, it transitioned. And that whatever existed before still whispers through the cracks of space-time, shaping everything we think we understand.